If you're studying energy as it applies to chemistry, you eventually realize there's a whole bunch of letters. Let's take a look at some and see if you can remember what they stand for. We've got G for free energy. What's K? Well, that goes back to equilibrium. R, just a number, it's a constant. There are two different versions of it, the 0.0821 version and the 8.314 version. S stands for entropy, T for temperature, H for enthalpy, C, perhaps it should be little c, that's specific heat, and Q simply means heat. Okay, let's think about the relationship between free energy and equilibrium. There is a formula, but let's just take a look at it qualitatively first. Say you got a non-spontaneous reaction. It's not occurring. That means delta G is positive. And that probably means you have a lousy K value. That would mean less than its equilibrium value. I'm going to say low. If you're at equilibrium, delta G by definition is zero. You're neither spontaneous nor non-spontaneous. You're right on the edge. And K would be variable, meaning look it up. There should be data on that. It could be a terrible number. For example, weak acids have a lousy equilibrium, or it could be very high. One way to also do it is just to plug into a formula. This is the one that's most often used. Delta G equals RT times the natural log of K. So that's free energy for G, a number for R. And since it's an energy number, R should be 8.314 joules per Kelvin mole. T should be the temperature in Kelvin times the natural log of K, which is the equilibrium constant. It can be re-expressed here to solve for K, since that's oftentimes what you need to do. Okay, let's fill in this table. It's a spontaneous reaction. Tell me about delta G. Ooh, it's negative. Tell me about K. Well, it's doing better than its equilibrium value. If you're neither, I guess you're at equilibrium. Delta G is zero and K is available. Look it up. It's non-spontaneous. Not good. It's not occurring. What's delta G? Positive number. What's K? It's lousier than its equilibrium value. Okay. We mentioned before which R we should use. If it's a gases question or if there's no energy involved, I would certainly use, oh, I'm a little out of order here. There it is, 0.0821 liters atmosphere divided by mole Kelvin, the picky version of R. Every piece of data in an equation that uses this form R must be in those units. If you got energy involved, and this is the energy unit, I would use 8.314 joules per mole Kelvin. There is some data that occasionally shows up with a different unit. This is kind of archaic, but you may find this. It's 1.987 calories per Kelvin mole. I don't like to use this for a couple reasons. One, it's pretty uncommon, and two, the calories with the small c is not the same as a nutritional calorie. It's a scientific calorie, and it's 1,000 times smaller. However, since 4.184 joules does equal one of these scientific calories, you can see when you multiply this by 4.184, you get the normal version of 8.314. So I'd recommend just using that. Relating free energy, enthalpy, entropy, and temperature, I am reminded of the free energy formula, delta G equals delta H minus T delta S. However, we can say that a reaction that is exothermic and shows an increase in entropy has got to be spontaneous always. This is one of those negative, 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 positive kind of questions, but exothermic means delta G means that the enthalpy is favorable. It's negative. And if it's increasing in entropy, it's getting more random than delta. Then S is positive, and it gets subtracted to get G, and therefore both of those numbers will end up making it more negative, so the reaction, regardless of those values, has to be spontaneous. This is energy and making sense of all those letters.